Hello and welcome to this Copernicus Marine Service tutorial for Northwest Shelf Physical Products. My name is Robert McEwen. I'm a Shelf Sea scientist working in the Met Office in the UK. I'll be demonstrating how you can explore some of the physical products available from the Copernicus Marine Service using the Python programming language within a Jupyter Notebook. Jupyter Notebook is an open source web application that allows you to work interactively with code and visualize data. The notebook is made up of a series of cells that contain either text and images or sections of code. You can execute the cells by either using the play button from the top menu or using the keyboard shortcut Shift and Enter. This notebook will concentrate on current data from the North Sea. It will contain 3 different exercises. First, we will visualize residual surface currents from daily mean products. We will then use hourly data to visualize currents through the water column, and then we'll look at the impact that tidal currents have on other surface variables. The data used in these exercises has already been downloaded from the Copernicus Marine Service using the subsetter tool and are stored in this file data. However, the techniques used will be applicable to any data you choose to download yourself. Detailed information on the product used in these exercises can be downloaded from the Copernicus Marine Service catalogue. The first thing we have to do before we can start our exercises is import the relevant tools that we'll be using throughout this notebook. The main libraries that we'll be importing are OS, NumPy, Xarray, Matplotlib and CartipHy. These will help manage our directory structure, perform calculations, access our data, plot our data and plot geospatial data. This is the first code cell that we're going to run. First we'll click on the cell and then click the play button. Once a number has appeared in these brackets, we can tell that the code has been run. The objective of this exercise is to visualize the residual current patterns within the North Sea. The data that we'll be using comes from the real-time forecast product. We'll be using daily mean data covering a large area of the North Sea. We'll be looking at surface data. The current surface data is broken down into U and V components representing eastward and northward current velocities. We'll be looking at data that covers a period of 1 day. The first thing we need to do is define some parameters that we'll be using in this example. Firstly, fname is the name and path where the data file is stored. Path out is a path where the resulting figures will be stored. It is used to select the date that we wish to plot. Initially, we'll be plotting from the 10th of July 2020. U will represent our eastward current velocity and V our northward current velocity. From the Xarray library, we will now use the Open Dataset to open our file fname and store it in our dataset ds. We can then print a summary of this information. Here we can see the dimensions of our dataset, the variables that are within it, and some metadata describing the production of the file. We will now select a subsection of our data, constraining our depth to the surface and the time to the date we've selected. We'll then print a summary of the data. You can see here that the dimensions have been reduced to latitude and longitude, as we now only have a single depth and single time value. We're now ready to start plotting our data. For this we'll be using the matplotlib library. First we'll set the figure size, and then define the figure axes. For this we'll use CartoPy since we'll be plotting geospatial data. We can then set the axes extent. This will be our minimum and maximum longitude and our minimum and maximum latitude. We'll also be adding a coastline and land from CartoPy with a scale of 50 metres. We will then use the u and v components from the velocities to calculate the magnitude of the velocity vector. We can then use this with a stream plot to set our colour. We can then add a colour bar and set our axes. To show the image, we must use matplotlib.pyplot.show, and we can then save the figure. We'll set the file name to include the path to the results directory and the date that we've selected. As this code cell is running, we can see the star in the brackets. Once the number has appeared, we know that our code has run, so we can now view our plot. This plot of daily mean current streamlines shows us the circulation at this particular period in the North Sea. We can see that the strongest currents at the surface are located around the southern coast of Norway. You can now try to modify the code above and plot the surface currents for a different date. Where do the currents differ from the first plot? In the next example, we'll be looking at currents through the water column. We'll be using hourly data from the near real-time product. We'll be covering the same area as the previous exercise, but this time we'll be using data from the surface down to 600 metres. Our variables again will be the eastward and northward current velocities, and the time period we'll be looking at is a single hour from the 10th of July 2020. We will now set up the inputs for this exercise. Our file fname, the date we are selecting, and also a latitude and a longitude that we wish to plot from. We will then produce a figure showing the location of our point. This will use the CartoPy geospatial library to plot a map centred on our selected longitude and latitude. Here we can see the location of our selected point in the middle of the North Sea. We will now set the path to save our figures in, and also create two strings that we can use in naming of our files based on the latitude and longitude we've selected. We will now load the data from using the X-array package open dataset to load our file name into the dataset ds. From this dataset ds, we'll set our two variables, the v and u components of velocity, selected at our latitudes and longitudes. We'll also create a comparable set of data with value 0 to represent our vertical velocities, which are missing. We'll also select our depth from our U velocity. We'll then print a summary of these variables. Now that we have selected the data we wish to plot, we're ready to start generating our figures. Firstly, we're going to calculate the magnitude of our velocity vectors. This is so that we can set the scale of our plot to be the maximum of the magnitude. We can then set up our figure from the matplotlib pyplot figure and select the figure size we wish to plot. We can also choose our axes and make sure our projection is in 3D. We can then set a title. This will include the latitude and longitude of the location we'll be plotting. Since we wish our depth to go from the surface to the bottom, we will also invert the z-axes. Here we are setting the limits of the x and y-axes to be -1 times the maximum magnitude of our velocity to the maximum magnitude of our velocity, so that the arrowheads in our quiver plots will be scaled to the data. We're going to select from 3 different scale factors. This will be dependent on the maximum value of our data. We can then define appropriate tick value labels. We'll also label our axes with depth, eastward velocity and northward velocity. We'll then make a grid from which to plot our data on, using numpy.meshgrid. This will range from a value of -1 times our maximum magnitude to our maximum magnitude, in increments of 0.1. To plot our quiver, we must provide an x and y starting point. We'll also provide a z value scaled with our scale factor. We can then provide a u, v and 0 z velocities. We can also scale the length of our arrow and the line width. To show the figure, again we'll use matplotlib.pyplot.show, and we'll save the figure, including the location string. In the plot we've produced, we can see that the maximum magnitude velocity is at about mid-depth, and also that the direction of the velocity vectors changes through the water column. You can now try to use the code above to select your own location and plot another profile and compare this to the one you've already produced. How does the new plot differ, and what might explain this? In the last exercise, we will visualise the impact of tidal currents by plotting a time series of surface variables. In this exercise, we will use hourly data. We'll plot surface variables over multiple tidal cycles for locations with high and low tidal velocities. The dataset we'll be using is from the near real-time product. We'll be using currents, salinity, sea surface height, and temperature. The points we'll be looking at include a high tidal velocity area of the channel and a low tidal velocity area in the German Bight. We'll be looking at surface data for a period of 48 hours. This map shows the location of the high tidal point and the low tidal velocity point. We now have several files to define. We have a temperature file, a salinity file, a sea surface height file, and a current file. This is all for our first location. Our second location, these file names have been commented out using the hash character. We also define the path where we want to store our figures. And using xarray, we'll open their datasets and store this in DST, DSS, DSH and DSC. We can then print a summary of this dataset. To make sure our only variable dimension is time, we use isCell to select our latitude, longitude and depth, all to the 0 index. We'll now print a summary of this data for comparison. Here we can see that the only dimension that varies is time. These lines create the axis used for our quiver plots. We'll be setting a y-axis where all values for our quivers will be 0, and along our x-axis our quivers will be plotted at each hourly increment. We can now set up our figure, including our figure size and title. Our subplots, one for each variable, set up as follows. We will have a column of 4 plots, 1 plot wide, of which the first plot will be temperature. The colour of this line will be red. We use a similar setup for salinity, being plot 2, sea surface height, plot 3, and velocity vectors, plot 4. For this we'll be using the quiver plot. Lastly, we'll set a central baseline for our quiver plots and also set an X label and a Y-axis limit. Again, we can show a figure with matplotlib.pyplot.show. We can see here a number of tidal cycles shown in the surface temperature and salinity. Notice that the strong change in temperature compared to the trend over the 48-hour period. You can also see how sea surface height is very variable at this location, and that the velocity vectors are also very strong. Lastly, we can save our figure. You can now go back and modify the previous code to plot the time series for the second location and compare this to this plot. Hopefully you found these examples interesting. I would now suggest you try and download your own datasets from the Copernicus Marine Service subsetter and try running some of this code for areas you're particularly interested in.